Hello, chemistry students. We're now ready to review for our test tomorrow over solutions. I want to go ahead and first show you the makeup of this test. You'll have your usual 3 multiple choice type questions. There's going to be a matching section where I'll give you guys the words and then the definitions of these various ways that we measure up concentration. And so it'll be a one-to-one type thing. We'll also have a Henry's Law problem, a problem that involves molarity, a dilution problem, a problem that involves molality, a problem that involves freezing point depression, and then the 4 colligative properties. You're going to tell me whether it increases or decreases as you do something to the solution. And so what I'd like to do, I want to go ahead and go through examples of each of these types of problems, and so that way you'll have a better understanding of what to expect on the test. And so this test is going to be worth 50 points, and so it's one of our larger tests of the year. And so let us go ahead and get started with an example of a Henry's Law problem. All right. Henry's Law relates the solubility of a gas to its pressure. And if you don't remember, we have S1 over P1 equals S2 over P2. So this again is an expression of Henry's Law. So on the matching part of the test, one of the choices will say Henry's Law. This will be one of the other choices on the other side of the paper, so you would match this up with that. And so that will help you then to remember what Henry's Law is. And so let's go ahead and do an example of a Henry's Law problem right now. At 4.5 atmosphere, I'm sorry, I should say 1.5 atmosphere, my bad. The solubility of a gas is 0.54 grams per liter. So this would be an example of a mass to volume type concentration. Grams is a unit of mass, liters is a unit of volume. And so again, this is another way that you can express concentration. And so at 1.5 atmosphere, the solubility of a gas is 0.54 grams per liter. It's problem's asking for you to calculate the solubility when the pressure is doubled. All right, so let's take a look again at this question. Again, we're told that at 1.5 atmosphere, the solubility of a gas is 0.54 grams per liter. The question, what is the new solubility when the pressure is doubled? And so what we're looking for here in this problem is S2. So what we're going to do, I'm going to go ahead and rearrange this equation just a little bit. I'm going to move the P2 to the other side by multiplying both sides by P2. S2 is going to therefore be equal to S1 times P2 over P1. So again, I just went ahead and I rearranged Henry's Law to solve for S2, which is my new solubility. Now we're going to go ahead and plug in what we're given, and we should then end up with the correct answer. All right, so our first solubility, we're told here, is 0.54 grams per liter, so that's what's going to go here first. Our second pressure, and so notice that in this problem, it's telling us the pressure has been doubled. And so what is 1.5 times 2? It should be 3 atmosphere. So 3 atmosphere is going to go on the top here. And then on the bottom, our initial pressure, we're told, is 1.5 atmosphere. All right. And so to solve this problem, we can take our calculator, and we're going to go ahead and take 0.54 times 3 divided by 1.5. And so when I go ahead and do that, I end up getting an answer of 1.08. So 1.08 atmosphere. Good. Notice that solubility of a gas is directly related to its pressure. And so if we double the pressure, we should expect that the solubility will also double. And so notice that 0.54 times 2 is 1.08. So this does, in fact, follow Henry's law. All right, let us go ahead now and do an example of a molarity type problem. To remind you, molarity is the moles of solute over the liter of solution. So again, the definition of molarity, mole of solute divided by liter of solution, and again we use a capital M as its unit. All right, let's take a look at a problem that involves solving for molarity. And so here is our question. Calculate the molarity of a solution that contains 15.7 grams calcium carbonate dissolved in 275 milliliters H2O. All right, so the question here, calculate the molarity of a solution that contains 15.7 grams calcium carbonate dissolved in 275 milliliters of water. So notice again, the two things we need to know in order to solve this problem. We need to know the moles and we need to know the liters. And so right now, we have this in terms of mass. And so what we need to do is we first need to figure out the molar mass of the calcium carbonate. So we need to do that first. Notice that the formula for calcium carbonate, we have 1 calcium, we have 1 carbon, and we have 3 oxygens. And so we use our periodic table. We know that calcium is approximately 40 grams per mole, carbon is roughly 12 grams per mole, and each oxygen is 16 grams per mole. So we need to go ahead and do the math first. So 40 grams per mole plus 12 grams per mole plus 3 times 16 grams per mole. So this represents the calcium, this represents the carbon, and then these are the 3 oxygens. So let's go ahead and calculate then the molar mass of the calcium carbonate. And so when I do that, I end up with a nice even 100 grams per mole. So this is going to equal 100 grams per mole. So my first step in this problem is to convert this mass then into moles. And so now that we have the molar mass, it's going to make this very easy. We have 15.7 grams of calcium carbonate times, we're going to put the 100 grams on the bottom so that the units cancel out. The 1 mole therefore goes on the top of the fraction. So we have 1 mole CaCO3 on top, 100 grams CaCO3 on the bottom. Notice that because we're dividing by 100, we only need to move the decimal place to the left twice. 1, 2. So it's going to be 0.157 mole of CaCO3. All right. And so now what we need to do, we have the mole. We don't have the liters. However, we do have the volume in terms of milliliters. And so we can convert easily enough because we remember that there's 1,000 milliliters in a liter. And so I'm going to convert this now from milliliters to liters. I'll put the 1 liter on top. The 1,000 milliliters goes on the bottom so that the units cancel out. Because I'm dividing by 1,000, I just need to move the decimal place to the left 3 places. So we have 1, 2, 3. So this is going to be 0.275 liters, and this represents our water. Now that we have both the moles and the liters, we simply take this number divided by that number, and that should give us the concentration in terms of molarity. And so our molarity is going to be 0.157 mole divided by 0.275 liter. And so I need to use my calculator to solve this. So we have 0.157 divided by 0.275. And so when we do that, we're going to end up with something roughly about 0.57. So notice we use the capital M to signify the fact that this is molarity. And so our final answer here is 0.57 molar. And so that would be an example of how to do a molarity problem. So remember, you have to have moles, you have to have liters. We had to first go from mass to moles using the molar mass of this compound. We converted the milliliters to liters, knowing that there's 1,000 milliliters in a liter. Then once we have these two numbers, we take this number, divide by that number, and that gives us 0.57 molar. All right, let us now take a look at how to do a molality problem. And so we have to remember molality is different from molarity. All right. So molality, we're going to use a lowercase m for its unit. So molality, lowercase m, it's the moles of solute divided by the kilograms of solvent. Mole of solute divided by kilogram of solvent. All right, and so on this part of the test again, I would say molality, and then you'd have to match it up then with this definition. All right, and so notice what the molarity and molality have in common. This top number is the same. However, with molality, the bottom number is now kilograms of solvent. And so remember, in a solution, the solute is what gets dissolved. The solvent is what is doing the dissolving. And so let us take a look at how to do a molality type problem. All right. Question. What is the molality of a solution that contains 75.3 grams potassium chloride in 95.0 grams water? All right, so again, the question here, what is the molality of a solution that contains 75.3 grams KCl in 95.0 grams of water? And so notice again, we need to first find the moles of solute. We can convert this then easy enough to kilograms. Once we have the moles in kilograms, then we'll do this math and then we'll get our answer. So let's go ahead. Notice again, we need to first figure out the molar mass of the potassium chloride. So let's go ahead and we'll do that first. Notice that the formula for potassium chloride, we have one potassium and we have one chlorine. And if we look at our periodic tables, we see that potassium is approximately 39 grams per mole, chlorine is approximately 35, and so we take 39 grams per mole plus 35 grams per mole. And so when we go ahead and we do that, we're going to end up with 74 grams per mole. And so that is our molar mass of our potassium chloride. Now what we need to do, we're going to convert this mass to moles, so 75.3 grams KCl. On the top, we'll put the mole, and therefore on the bottom will be the 74 grams of KCl. All right. So we're going to go ahead and take 75.3, divided by 74, and we end up with something about 1.02. All right. And this should hopefully make sense because, again, we see that this is 74. This is just slightly above that, so we expect that we're going to have slightly more than 1 mole, and in fact we do. All right. Now what we need to do is we need to convert the grams of water to kilograms of water. And so remember that there are 1,000 grams in 1 kilogram. And so we'll go ahead and convert this, 95.0 grams of water times, and so we'll put the 1,000 grams on the bottom so that the units cancel out, and the 1 kilogram of water goes on the top. For this problem, just like the last one, we're dividing by 1,000, which means we need to move the decimal place to the left 3 places. 1, 2, 3. So there's going to be another 0 here. So this is going to be 0.095 kilograms of water. And so we now have our moles, we have our kilograms, and so now we're ready to finally solve this problem. So our molality, we're going to take 1.02 mole, and we're going to divide that by 0.095 kilograms. And so we're going to go ahead and punch that in our calculator. 1.02 divided by 0.095. And so when we do that, we're going to end up with something that is roughly, let's say, 10.7 molals. So this is going to be roughly 10.7 little m. All right. I want to remind you, as always, rounding will not be counted against you. So if you showed me your work and you got the final answer and you rounded this up to 11, I would be totally fine with that. And so again, the rounding will not be counted against you. It is, however, important to show your work, get the answer with the right unit, and then make sure to circle or box it in. And so the answer for this problem, this solution is 10.7 molal, which we use the lowercase m for. All right, let us now go ahead and do an example of a dilution type problem. Dilutions, as we discussed before, are amongst the most useful type in the chemistry lab. And so, again, when I was doing research up in Columbus, I used the dilution equation almost every single day. All right. A dilution, we have a stock concentration, we have a dilute concentration, and so we have M1 times V1 equals M2 times V2. So remember, M stands for molarity and V stands for volume. And so this would typically be our stock concentration, and this over here would be our dilute concentration. And so let us go ahead and take a look at an example of a dilution problem. All right. The question, how many milliliters of 3.0 molar H3PO4 can be made from 95 milliliters of 5.0 molar H3PO4. All right, so here's the question for dilution. How many milliliters of 3.0 molar H3PO4, that's phosphoric acid, can be made from 95 milliliters of 5.0 molar phosphoric acid? So in this problem, what we're looking for is the V2. So I'm going to go ahead and rearrange this equation just a little bit. I want to move the M2 to the other side of the equation. I'm going to divide both sides by M2, and so I can say that V2 is equal to M1 times V1 over M2. All right. My initial stock concentration, I'm told, is 5.0 molar, so I'll put that here. We also have 95 milliliters. I'm going to go ahead and save myself the work because if you notice, we are looking for the volume in milliliters. I'm going to keep this, therefore, in terms of milliliters. So I'm going to put 95 milliliters on top. I'm going to then divide this by our second concentration, which was our dilute concentration. This is going to be 3.0 molar. All right. You'll see why I kept it in terms of milliliters. The molars cancel out. You're left with milliliters, and so it's going to then set up this problem to solve the volume in terms of milliliters. And so we'll go ahead and use our calculator. We'll have 5.0 times 95 divided by 3.0. And so when I go ahead and I do this in my calculator, I see that I end up with approximately 158 milliliters. All right. All right. So what this means, if I were to draw out 158 milliliters of the stock concentration, I can then use this then to make up this concentration of phosphoric acid. So remember, you can only dilute down, so it's going to always go down. All right, and so that is an example of a molarity problem. All right, I want to go ahead then and do one more type of problem, and this problem is going to involve a freezing point depression. And so we'll go ahead and do that. And so remember that one of the colligative properties, freezing point depression, occurs when you add solute to a pure solvent. It will cause the freezing point to be lowered. And so we're going to go ahead and put up the equation for this. So freezing point depression. We use the Greek symbol delta to indicate change. So our change in temperature for freezing, the lowercase f, is equal to some constant for freezing times molality. So notice in this case we're using the lowercase m to signify that this is molality. And so let's go ahead and take a look at a problem that involves us calculating freezing point depression. The question: calculate the freezing point of 12.1 grams of naphthalene, which is C10H8, which of course you would not have to memorize, dissolved in 0.175 grams of benzene, which is C6H6. And the book tells us to refer to table 6 for the needed data. And so I need to go back in this chapter to find table 6. And so for table 6, this is the table that they're referring to. I would, of course, provide you with the constant on the test so that you would not need to worry about that. We're told, however, that the freezing point depression constant for benzene is 512 degrees Celsius per mole. So our K sub F is equal to 5.12 degrees C per mole. So this is specific for benzene. So I use the table in the book to do that. I will, of course, give you guys the constant on the test, so you don't have to obviously look it up. All right, this one's pretty easy. All we need to do is we need to, first of all, figure out what the molality of this solution is. And so remember that molality, we'll put up here, is the mole of solute over the kilogram of solvent. And so Our solute in this case, what's being dissolved, is the C10H8. And what the solvent, what's doing the dissolving, is the benzene, which is the C6H6. So we need to make sure to keep those straight. All right. Notice that we need to first calculate the moles of the naphthalene. And so we have it in terms of grams. So once again, we need to find the molar mass of the C10H8. The formula for naphthalene, we have 10 carbons, we have 8 hydrogens. We look at our periodic table. We know that carbon is approximately 12 grams per mole. Hydrogen is only 1 gram per mole. To find the molar mass, we take 10 times 12 grams per mole plus 8 times 1 gram per mole. 10 times 12 is 120. 8 times 1 is 8. 120 plus 8 is 128 grams per mole. All right, so we have the molar mass now of the naphthalene, and so now we can use this conversion factor to go from grams to moles. We're told that we have 12.1 grams of the C10H8. We'll put the 1 mole of the C10H8 on top. The 128 grams of C10H8 goes on the bottom. And so to solve this part of the problem, we're going to go ahead and take 12.1 and we're going to divide that by 128. And so when we do that, we're going to end up with approximately 0.09 moles. All right. Next thing we need to do, we need to convert the grams of the benzene into kilograms. So remember again, there's 1,000 grams in 1 kilogram. And so we have our 0.175 grams of C6H6. A kilogram of C6H6 will be 1,000 kilograms, or 1,000 grams. And so again, to divide by 1,000, we just move the decimal place to the left 3 times. So 1, 2, 3. So we're going to end up with 0.000175 kilograms of the C6H6. And so now we're ready to go ahead and calculate the molality. The molality is going to be 0.09 mole divided by 0.000175 kilograms. And so we'll go ahead and do that. And so we end up with a molality of about 514. All right. Then what we need to do is now we need to go ahead and use this then to solve for the last part of this problem. And so, I shouldn't have done that last step. I apologize. This was actually already in terms of kilograms, so you don't have to do this last step, fortunately. So I apologize for that, guys. And this is important why you should always read the problem carefully. And so we actually can just go ahead and take 0.175 kilograms. So again, make sure you read the questions carefully, please. All right. And so 0.09 divided by 0.175 is 0.51 molal. And so again, I apologize for that. Finally, now that we have the molality, we have our constant we're provided from the book. To find the change in temperature, we use this equation. Delta T sub F is now going to be equal to this 5.12 degrees C per molal. We're going to multiply this by 0.51 molal. You'll see that the molalities cancel out. So finally, our problem, 5.12 times 0.51 And so we end up seeing that the temperature is going to drop roughly 2.6 degrees Celsius. All right. So what this means, if we look up in the table what the freezing point for this naphthalene is, we would have to subtract 2.6, and that would give us the new freezing point. And so this, again, is an example of a freezing point depression. And so hopefully that all made sense. I hope you guys have a good rest of your day, and I want to wish you all good luck for tomorrow's test. And thank you.